All right, good morning. So, as we said at the beginning of the class, in the first few weeks we said we would sort of see how we can model problems as an optimization problem, as a linear programming problem more precisely. And so far we have seen many examples, many different examples coming from different settings that can be cast as an LP problem. And before I move on, I just would like to sort of recall the three assumptions of LP. So, So remember, like a couple of weeks ago, I think it was last week, we actually sort of stated a number of assumptions. So more precisely, we stated three assumptions that should be satisfied by a problem in order for it to be modified or to be modeled as an LP problem. So the assumptions were the following. So the first one was proportionality and additivity. The second one was divisibility. And the third one was certainty. So these were the three assumptions that should be satisfied by a problem so that it can be modeled as an LP problem. Okay? Proportionality and additivity, remember, actually tell you what the objective function and the constraints should look like. So both the objective function and each of the constraints should be of the following form: a constant times a variable, plus a constant times a variable, and so on and so forth. And in the constraint, we can have either less than or equal to, or greater than or equal to, some other constant on the right-hand side. So divisibility basically means that our decision variables should be fractional, should be allowed to be fractional. Okay? And certainty means that we should know everything in advance. Okay? So we should know everything for sure, so there's no randomness involved. And then we define another class of optimization problems in which, among these three assumptions, only the second assumption is not satisfied. So if only the second assumption is violated, so what is the second assumption? The divisibility assumption is violated. We actually call it, and then we have an integer programming problem. And we use IP for short. So therefore, the main difference between an IP problem and an LP problem is that in an LP problem, all your variables should be fractional, should be allowed to be fractional. Okay, so all decision variables should be divisible in other words. On the other hand, in an IP problem, we don't have divisibility in at least one of the decision variables. Okay, so for example, I gave you several examples earlier. So if xi denotes the, for example, number of cars of model I, for example, produced by a manufacturing facility, then obviously we cannot have fractional values, right, in terms of number of cars. So as a result, if among these three assumptions only the second one is violated, then we have an IP problem or integer programming problem. Okay? Now, so far, all the examples we have seen satisfied all of these three assumptions so that we could actually model them as an LP problem. So from now on, we're going to look at some problems in which among these three assumptions, the first one is satisfied, the third one is also satisfied, but the second one is not. Okay, so in other words, we're going to look at problems that can be cast as an integer programming problem. Okay, so we're going to see some examples, and we're going to try to understand what kind of problems can be cast as an IP problem. Okay, and what the difference between IP and LP is basically. So from now on, as I said, we're going to look at the following models. So we're going to look at integer programming models. So once again, all the examples that we have seen so far actually could be modeled as an LP problem because all the three assumptions were satisfied. So from now on in the problems that we're going to look at, the second assumption will not be satisfied, okay? But the first one and the third one will be satisfied. And such problems can be cast as IP or integer programming problems, okay? So I'm going to start with a simple example. So example number 11. So this problem is known as bus scheduling problem. And suppose that we are given the following information. So So we are given periods starting from 1 to 6. And then here are the hours. So essentially, we assume that a 24-hour period, a single day, is divided into 6 periods, and each period actually lasts for 4 hours. Okay, starting from midnight to 4 a.m., 4 a.m. to 8 a.m., 8 a.m. to 12 a.m., and so on and so forth. And then somebody gave us the following information. So the minimum number of buses required in period 1 is 4. In period 2, it's 8. In period 3, it's 10. In 4, it's 7. In 5, it's 12. And in 6, it's equal to 4. So suppose that you actually studied the demand for public transportation, and you realize that, for example, in the first period, which goes from 12 a.m. to 4 a.m., from midnight to 4 a.m., 4 buses would be enough to satisfy the demand. Okay? Then in second period, you need 8 buses. Then 10 in the third one, and so on and so forth. So we have the following assumptions. So each bus starts to operate at the beginning of a period, and operates for 2 consecutive periods. In a 24-hour period. In a 24-hour duration, let's say. So what does that mean? So essentially, for example, if a bus starts to operate at 12 at midnight, then it operates for the first hour and the second hour, and then, for example, it goes into maintenance. Okay? And the next day, it can again start at 12 a.m., and then, again, it operates for 8 hours, and then it goes for maintenance, and so on and so forth. So consecutive basically means back-to-back, right? So if it starts in the first period, then it works for the first and the second period. And if it starts working in the third period, then it works for third and the fourth period. If it starts at the beginning of sixth period, then it's going to work for sixth and the first period. Okay, so we have a sort of cyclic schedule, basically. So the question is the following. So find the minimum number of buses to satisfy the demand. So how many buses should I use to satisfy the entire demand? So once again, let me actually draw you a picture, so just to make it easier to understand. So suppose that this circle represents a day, okay? And so here is 12 midnight, and over here is 4 a.m., then here is 8 a.m., then we have noon, and then 4 p.m., and 8 p.m., okay? So I'm actually dividing a day into 6 equal periods. Okay? And for example, if a bus starts operating here, then it's going to operate for 2 consecutive periods. So it's going to actually work until 8 in the morning, right? So in other words, or as another example, so if a bus starts operating here, then it's going to operate for 2 consecutive hours. So it's going to operate until 8 at night. Okay? And the question is the following. So for each period, I'm actually given the minimum number of buses required. So in the first period, I should have at least 4 buses operating. In the second period, I should have at least 8 buses, and so on and so forth. And the question is, so what's the smallest number of buses I need so that I can satisfy the demand? Okay, so what's the smallest number of buses I should sort of buy or rent so that I can actually satisfy the demand of public transportation, let's say. Okay? So first of all, is the problem clear? All right, so how should I approach this problem? So how should I define my decision variables? So remember, my goal is to minimize the number of buses that I need. So what can I control in this problem? The number of buses that sort of operate in each period, for instance, right? Okay, so that's something I can control. So how should I define my decision variables? So here's one idea. What I can do is I can define xi to be the number of buses operating in period I, right? And since I have 6 periods, I'm going to have 6 decision variables. So x1 denotes how many buses are operating in the first period, x2 denotes how many buses are operating in the second period, and so on and so forth. So this is something I can control. Okay. All right, what's my objective function? So I'm trying to minimize the total number of buses that I need. So how can I express my objective function? So I can add them up, right? So basically, I'm going to minimize the following. So I'm going to minimize x1 plus x2 plus all the way up to x6. Okay. Subject to, what are my constraints? Well, in each period, I should make sure that I'm going to need at least the required number of buses, basically, right? Okay, so for example, for the first period, what's my constraint? x1 equals, well, x1 is greater than or equal to 4, basically, right? So basically, in the first period, I should have at least 4 buses. Okay? What about second period? So x2 is at least 8. Then x3 is at least 10. x4 is at least 7. x5 is at least 12. And x6 is at least 4. So these are the sort of restrictions that I have for my problem. And remember, xi denotes the number of buses, so xi is not divisible, basically, right? So as a result, this problem actually violates the divisibility assumption because we cannot have 2.5 buses, for instance. Okay? So as a result, the decision variables xi are not divisible. So in other words, they should only take integer values. So to signify that, we're going to add the condition that xi is integer. Okay, just like we did earlier for some of the problems. So each of the xi's, x1 through x6, can only take on an integer value. Okay? All right, any questions? So in this problem, as I said, I mean, the objective function looks like an LP objective function. The constraints they look like LP constraints. The only difference is that my variables are no longer divisible, right? So as a result, I should add the extra condition that xi can only take integer values. And as soon as we have that, we're looking at an IP problem rather than an LP problem. Okay? Any questions about this? Well, actually, this formulation is not correct. Okay? So can anyone see why it's not a correct formulation? So here's what the problem is with this formulation. Okay, so how am I defining my decision variables? x1 is the number of buses that are operating in the first period, right? Okay, and x2 is the number of buses that are operating in the second period. Okay, and I'm pretending that these two are completely different from one another. Okay, so for example, I'm assuming that x1 and x2 are completely independent of one another in this formulation. Whereas in practice, in real life, so basically some of the buses that are operating here also actually operate in this period as well. Okay, so similarly, some of the buses that operate here also operate in this period. So number of buses operating in different periods actually depend on one another. They're not independent. Does everybody see that? Okay. However, in this formulation, I assume that, for each period, I have a different number of sort of buses that are operating, and they're independent of one another. And that's not correct, actually, in this problem. Let me repeat that again. So in the current formulation, I'm assuming that in each period, the number of buses operating is independent of one another. Okay? So x1 is independent of x2, which is independent of x3, and so on and so forth. Whereas if I look at the problem, it tells me that if a bus starts operating here, okay, it actually operates for 2 consecutive periods, right? So which means that if a bus operates in this period, then the same bus will also operate in this period. Okay? What does that mean? Well, I meet the demand of one bus in this period and in this period with the same bus, actually. Okay? Whereas in this formulation, actually, I'm not considering that. So in this formulation, I'm just pretending that, you know, the buses that operate here are different from the buses that operate here. Okay? In other words, in this formulation, there's actually overcounting. Okay? So I'm actually, in this formulation, I'm using more buses than I need. Okay? So the question is, how can I fix my formulation? So before that, is the problem clear? So is the problem with this formulation clear? Any questions? All right. So the question is the following. So this is the incorrect formulation. Okay? And the question is, how can I actually fix my formulation? So okay.
For example, we need 8 buses, 8, 2, 4, 2. So 8 is greater than 4 and it will cover that. So maybe we can say that.
Okay, but there's one problem still. So for example, in x1 in this formulation, okay, so for example, x1 is equal to 5, let's say. Okay, just as an example. If x1 is equal to 5, then among those 5 buses, some of them actually started operating here, and some of them started operating right here. Okay? And the problem is, I don't know which one actually started here and which one started here. Okay?
Can we change the decision horizon?
Okay.
We can say xi, number of buses starting operation in period I equal to.
Excellent. So that's exactly how I'm going to actually change my decision variables, and you're going to see that that's going to fix our problem. So here's a new formulation. So just to make it different, I'm going to call it yi. So this is going to be the number of buses starting to operate at the beginning of period I. And I goes from 1 to 6. So note that I changed my decision variable now. Okay, so I'm now counting the number of buses that start to operate at the beginning of a period. Okay? Now what's the effect of this change? Well, so what's my objective function? So I want to minimize the number of buses that I'm going to use. So how can I express that in terms of decision variables? So what's my objective function, in other words? So I'm minimizing the total number of buses I'm going to use. So how can I express it as an objective function? So well, just like we did earlier, we can actually minimize the sum of y1 plus y2 plus all the way up to y6. Okay? So the total number of buses that I'm going to use will be equal to number of buses that start to operate in the first period plus number of buses that start to operate in the second period, and so on and so forth. Okay? Of course, here I'm just making a crucial assumption, as I said earlier. So, for example, if I use a bus, or if a bus starts to operate here, it operates for 8 hours, and then it goes to maintenance. Okay? And then next day, it can actually do the same thing again. Okay? So in other words, I can use a bus only for 8 hours in a day. Okay? I can use the same bus for only 8 hours in a day, and then, you know, that bus actually goes to maintenance, or it goes somewhere else, and so on and so forth. That's the assumption. Okay? So as a result, the number of buses I'm going to need is precisely the number of buses that start to operate here, plus here, and so on and so forth. Okay? So that's exactly my objective function. Now, how can I express my constraints? Well, so let's think about the demand of the first period, for instance. Let me go back to my picture again. So this is my first period. And I need to make sure that I have at least 4 buses in that period. Okay? So the only thing I need to figure out is actually which buses are counted in this period with respect to my decision variables. Okay? Well, so there are buses that start operating here, which will actually be active in this period. What else? Well, there are also buses that started here that will also be active as well. Okay? So basically, in terms of number of buses in the first period, there are 2 sources, basically, right? So there are those buses that started operating earlier, and there are those buses that just started operating in this period. So how can I figure out the total number of buses? I'll just add them up, basically, right? So what's the total number of buses I need in this period, or I have in that period in terms of my decision variables? Y1 plus Y6, basically, right? So that's exactly the number of buses that I'm going to need, or I'm going to use. So Y1 plus Y6 should be at least 4. Okay? So I need to make sure that I have at least 4 buses actually operating in the first period. Then let's look at once more, and then from now on we're going to do it sort of more generally. What about the second period? So what's the total number of buses I'm going to use? So it's going to be Y1 plus Y2 basically, right? So the buses that start operating earlier plus the buses that just started operating in this period. Okay, so I'm going to add up these 2 numbers. So, and that number is equal to Y1 plus Y2. And Y1 plus Y2 should be at least 8, basically. Okay? And then I'll look at period 3. So what's the total number of buses I have in period 3? Y2 plus Y3, basically, by the same reasoning. So Y2 plus Y3 is at least 10. Then in the fourth period, I need 7 buses. So Y3 plus Y4 is at least 7. Then in the fifth period, Y4 plus Y5 is going to be at least 12. And in the sixth period, Y5 plus Y6 is at least 4. So these constraints ensure that I meet the demand, basically. Okay, I have at least a minimum number of buses in each period. Any other additional constraints? Yi should be non-negative, that's good. So Yi is greater than or equal to 0 for all I. Anything else? Yi should be integer valued, that's also important. So Yi is integer valued for all I. So now this is the correct formulation of this problem. Okay, so in the previous problem, as I said, we pretended that the number of buses in each period are independent of one another, and that's not true actually. Okay, so number of buses in one period actually does affect number of buses in the second period, and so on and so forth. Okay, and that relationship is taken care of by the corrected formulation. Any questions? Does everybody see why the first one was wrong and the second one is correct? Any questions? Yes.
We continue with that assumption. I mean, the first one. How can we make it correlate with that decision variable?
Oh, I cannot. I cannot. No. So with those decision variables, I cannot formulate the problem. Okay? Which basically means the following. So when you're formulating an LP or an IP problem, you should define your decision variables correctly and carefully. Okay? And if you define your decision variables in the wrong way, then you cannot actually save your formulation. Okay? So if I actually define my decision variables that way, there's no way I can formulate the problem. Okay? Other questions?
Y5 and Y6 4 olacak dedik en az. Peki 5 ile 12'si nasıl karşılanacak? 5'te 12 tane otobüs gerekiyor yani.
Neyle oturtuyorsun?
Evet.
So Y4 plus Y5 should be at least 12. So basically, what does this constraint mean? Well, I'm looking at period number 5, which is this period. So number of buses operating in this period will be number of buses that start operating here, which is Y4, plus number of buses that start operating here, which is Y5. So the sum of these two will be the number of buses in this period. Okay? And that should be at least as large as 12. Other questions? All right. So if not, then I'm going to move on to the next problem. So once again, this is a problem in which the divisibility assumption is not satisfied. Okay. And as a result, this is an IP formulation. So this is an IP problem. Okay. So this is not an LP problem because the YIs are not divisible. However, the other two assumptions are satisfied. So as a result, we have an IP problem, not an LP problem. Okay. All right. So example 12. So this is known as workforce scheduling. And suppose that we have the following problem. So let's say Burger Queen would like to determine the minimum number of kitchen employees. And then similarly, we have the following information. So here are my days. And here are the minimum number of workers. Workers required. So on Monday, which is the first day, let's say, I need at least 8 employees. On Tuesday, which is the second day, I need at least 6 employees. On Wednesday, which is the third day, I need at least 7 employees. On Thursday, which is the fourth day, I need at least 6 employees. On Friday, which is the fifth day, I need at least 9 employees. And on Saturday, which is the sixth day, I need at least 11. And on Sunday, which is the seventh day, I need at least 9. So once again, based on the demand, suppose that somebody gives me this information, this data, okay? So this is the smallest minimum number of kitchen employees that I should have so that I can meet the demand every day. So each employee works 6 days a week and takes the second day off. Takes the 7th day off, sorry. So the question is similar. What's the minimum number of employees? What is the minimum number of total employees that should be hired? So this kind of similar problem. So instead of looking at sort of number of buses, we're looking at number of kitchen employees. So we have 7 days of the week, and in each day we have the minimum number of sort of workers required. For example, on Monday we need at least 8 workers. On Tuesday we need at least 6, and so on and so forth. And the question is the following. So what's the minimum number of employees I should hire so that I can meet the demand? So I can make sure that on each day of the week, I'm going to have at least the minimum number of employees I need to sort of carry out my business, basically, okay? So once again, is the problem clear? So one important assumption is the following. Each employee works 6 days a week and takes the 7th day off. And we assume that the employee can pick actually whichever day he or she's going to pick off. Okay, so for example, some employees may take Wednesday off, some employees may take Saturday off, and so on and so forth. Okay. So as a result, we give the employee a chance to pick his or her day off, basically. Okay. All right. So how can I formulate this problem? What are my decision variables? Well, so how should I define my decision variables?
Can it be the same type of previous problem?
Exactly. So it should be something similar to this one as well. Okay. So once again, if you try to formulate the problem in terms of number of workers, for example, working on day I, okay, then you're going to have the same problem as you had here. Okay. Why? Because I mean, number of workers working on Monday and the number of workers working on Tuesday are not completely independent of one another. Okay. Because some of the workers that work on Monday will also work on Tuesday and vice versa. Okay. So as a result, you need to be careful. And as I said, if you define your decision variables xi to be the number of workers working on day I, and I can go from 1 to 7, then this is going to be wrong. Okay? It's going to be wrong by the same reasoning. Okay? So again, here you pretend that you assume that number of workers working on each day is independent of one another, whereas it's not actually. Okay? As I said, I mean, some people that work on Monday will also work on Tuesday, and they will also work on Wednesday, and so on and so forth. Okay? So there's some relationship between number of workers working on Monday and working on other days. So how should I define my decision variables? Well, how did we fix the problem here? Well, we defined our decision variables differently, basically. Okay. So how should I define my decision variables for this problem? Okay, so that's one way of doing it is the following, just like we did here. So we can pretend that, you know, in a week there are 7 days, right? So, okay. And some people start working here and then, for example, work for 6 days and take the second day off. Some people start working here and then they work until here and so on and so forth. Okay? So this is one way of doing it, and that would be exactly like defining it this way. Okay? However, there is a sort of essentially the same formulation, but it's sort of I can define it in the following way as well. So for example, let me define yi. So this is again the wrong formulation. Okay? So yi will be the number of workers who are taking day I off. And I goes from 1 to 7. So what does this mean? For example, y1 is the number of workers who are not working on Monday. Okay? So who are not working on Monday, but they are working on every other day, basically, right? And y2 is number of workers who are not working on Tuesday, but they work on every other day. Okay? So this is essentially the same as formulating it that way, basically, right? Okay? So number of workers who are taking Monday basically the same as number of workers who are starting to work on Tuesday. Does everyone see that? So it's essentially the same sort of definition. So as a result, I can define my decision variables this way. So yi is the number of workers taking day I off. And now I can formulate my problem. So what's my objective function again? What's my objective function? I'm going to minimize the total number of employees. How can I express it in terms of my decision variables? So I'm going to simply sum up all my variables. I'm going to have y1 plus y2 all the way up to y7. Okay, so indeed this is the total number of workers I'm going to need. Because once again, I mean, one thing you should be careful about is the following. So total number of employees can be thought of in terms of following classes. So basically, total number of employees is the same as number of workers who are not working on Monday, plus number of workers who are not working on Tuesday, and so on and so forth. And by doing this, I make sure that each employee is counted exactly once, basically, right? So I'm not counting anybody more than once here. Okay? Why not? Because basically, number of workers who are not working on Monday is completely different from number of workers who are not working on Tuesday. Okay? So there's no overlap, basically, between the two. Okay? All right, so what are my constraints? Well, let's start with Monday. On Monday, I need to make sure that I have at least 8 employees. So essentially what I'm going to do is the following. I'm going to look at the summation of all my variables which I can shortly write in this way. So basically, this is the total number of employees, right? And from this, I'm going to subtract y1. So what does this give me? So this is the total number of workers. These are the number of workers who are not working on Monday. So what's the difference? Number of workers who are working on Monday, basically, right? Okay. And I need to make sure that this is at least 8. So I need to make sure that on Monday, I'm going to have at least this many workers. Okay, so let me move on to Tuesday. So total number of workers minus y2 should be at least 6. Total number of workers minus who are not working on Wednesday should be at least 7. Number of workers, number of all workers minus number of workers who are not working on Thursday should be at least 6. Then number of workers minus number of workers who are not working on Friday should be at least 9. Then I from 1 to 7, yi minus y6 is at least 11. And finally, number of all workers minus number of workers who are not working on Sunday should be at least 9. And it's not too hard to see that these are valid LP constraints, basically, right? So if you write this out, basically, for example, from the first one, you have y1 through y7, sum of y1 through y7 minus y1. So you have y2 plus y3 plus y4 plus y6, y5, and so on and so forth. And that sum should be at least 8, and that's just like an LP constraint, right? A regular LP constraint. Yes?
Can we define the summation as another receiving variable and use it?
We can, but we don't need to. Okay? All right, any other constraints that I need? So never forget about non-negativity. Yi should be greater than or equal to 0 for all I. And since yi denotes the number of workers, so number of workers cannot be divisible. Okay, so as a result, yi should be integer for all I. All right, so let me, yes.
But they were able to choose any day. I mean, they weren't obliged to work in consecutive days. Like here, we are taking that if one worker starts working on Tuesday, then he has to work until Sunday. Maybe in a problem, let's say he starts working on Tuesday and works until Thursday and takes Friday off, then works the other days.
But then that employee will be counted in number of workers who are not working on Friday, basically, right? Okay? So basically, I mean, in this formulation, of course, we assume the following. We assume that we make a contract with the employee, and the employee says that I'm going to take Mondays off, and we're going to assume that that worker will always take Mondays off, basically. Okay? So that's not going to change. Yes?
If off days was not formal too, this decision variable is not valid, right?
Okay, so that's an excellent question. The question basically is the following. So suppose that instead of taking 1 day off, the employees were allowed to take 2 days off. Okay? 2 days a week. For example, I want to take Wednesday and Friday off. Okay? So the question is the following. How would I change my problem? How would I change my decision variables?
Maybe we can be taking it as 2 workers.
Let me ask the question again. So in this version of the problem, so each employee works 6 days a week and takes the 7th day off, right? So each employee takes 1 day off. And suppose that the regulations change, the laws change and so on and so forth. So basically, as an employer, you should give each employee 2 days off. Okay? So the question is the following. So how can I formulate the new version of the problem? So if I let each employee choose 2 days a week, okay, to take off, how would I change my formulation?
If worker, can a worker choose Tuesday and Friday, for example?
Yes. I'm assuming that the employee can choose any 2 days. Okay. For example, some Some workers can choose to take Tuesday and Friday off, for instance. Okay? Yes?
Can we assign why IJ is like first day and the fifth day off? And then can we assign like that?
Okay, that's a good question. So the question basically is the following. Can I change my decision variables in the following way? So instead of defining yi, I'm going to define yij with two indices. And yij will be number of workers who are taking day I and day j off. Okay? So for example, y15 will be number of workers who are not working on Monday and on Friday. Okay? So now, and that's indeed the correct formulation. Okay? So instead of having only one index, I'm going to have two indices. Okay? So I'm going to define, for example, y12 as number of workers who are not working on Monday and Tuesday. Okay? y15 will be number of workers who are not working on Monday and Friday. Okay? Then I need to just be careful about the constraints. Okay? I just need to make sure that, for example, to compute the number of workers on Monday, I can again add all the employees, minus I need to take care of every employee who's not working on Monday. Okay? So I need to look at y12, y13, y14, and so on and so forth. Okay? That summation should be subtracted from sum of all yij's. Is that clear? So essentially what I'm saying is the following. When I write down the constraints, I need to make sure that I need to take care of number of workers who are working on Monday carefully. Okay? And that can be calculated in the following way. I'm going to look at the sum of all employees. And from that, I'm going to subtract the ones who are not working on Monday. But unlike this formulation, number of workers who are not working on Monday will not be a single variable. But it's going to be like y12 plus y13 plus y14 and so on and so forth. Okay? It's going to be a sum again. So basically, I'm going to have a summation here minus another summation here. Is that clear? Okay? So as a result, the advantage of sort of this, defining your decision variables this way is that you can extend it to any number of days off. So for example, if your employees are allowed to pick 3 days off, for instance, okay, then, well, you're going to have yijk basically, right? Okay? So, you know, it extends in a straightforward way to any number of days off. Okay? Question, yes?
Number of at the edge basis too, then we're going to write 49 constraints. Right?
No, we'll still have...
1, 2, 3, or 2, 3, 2, 4.
No. So we'll still have same number of constraints, but each constraint will look differently. That's what I'm saying. Okay? So here we have again the sum of all variables minus the sum of workers who are not working on Monday. Okay? Instead of a single variable, we're going to have another summation here. Okay? So of course we're going to have sort of more decision variables than this one. We're going to have the same number of constraints, but the constraints will look differently. Yes?
And what about y23 or y32?
Okay, that's a good question. So what about y23 and y32? Well, you can assume that, for example, you only define yij such that I is always smaller than j. Okay? So, and are not equal to one another. So if you do that, then basically, you know, yij and yji are essentially the same, right? So as a result, you can pick one of the two. Any other questions? All right. Okay, so let me start defining the next problem, unless there are any other questions about this. So once again, these two are examples of IEP problems, integer programming problems, because in both problems, the divisibility assumption is not satisfied. In the first problem, we had number of buses, which are not divisible. Here we have number of workers, which are obviously not divisible either. So as a result, both of them actually give rise to IEP problems. Okay? So let me start defining the next problem, and then we'll take a break. And this is another example of workforce scheduling. So suppose that we had the following demand information for a shoe company. So we have the next 4 months, 1, 2, 3, and 4. And we have the demand in pairs. So in the first month, we have a demand of 300. In the second, we have 500, then 100, then 100. So this is our demand information for the next 4 months. Okay, so we have a demand of 300 pairs of shoes in the first month, 500 in the second month, and so on and so forth. And then we have the following information. So a pair of shoes requires 4 hours of labor. 4 hours of labor, and $5 worth of raw materials. Okay. We have 50 pairs of shoes in stock. And then we have a monthly inventory cost. So monthly inventory cost is charged for shoes in stock at the end of each month. At the end of each month, at $30 per pair. So the cost of keeping a pair of shoes in stock at the end of a month is actually $30 per pair. So currently we have 3 workers available. And the salary of each worker is $1,500 a month. Okay. So we have some more information. Each worker works for 160 hours per month. Works up to 160 hours per month. And then we can hire a worker. So hiring a worker costs $1,600. And then we can also fire a worker. So firing a worker also has a cost. Costs $2,000. And hiring and firing can take place at the beginning of each month. And the question is the following. So, how to meet the total demand? How to meet the total demand at a minimum total cost? So let me just quickly describe the problem and we'll take a break. So suppose that you're managing a shoe company, okay? And you have the demand for the next 4 months. And currently you have 3 workers available. And this is how much you pay each worker as salary, okay? Each worker can work up to 160 hours per week. And since the demand changes, you can hire and fire workers, okay, to sort of adjust your capacity, so to speak. So to manufacture a pair of shoes, you need 4 hours of labor and $5 worth of raw materials. Currently, you have 50 pairs of shoes in stock, okay? And if you have any sort of inventory at the end of each month, you have to pay $30 a pair for each pair of shoes. You pay $30 as inventory cost. You can also hire and fire workers because you can adjust the capacity. Basically, demand changes, so you have a lot of demand here, and then you have sort of much less demand. However, that's also costly, so you can hire a worker at a cost of $1,600 per worker, and similarly, you can fire a worker at a cost of $2,000 per worker. And you can make these decisions at the beginning of each month, basically. Okay? And the question is the following. So how should I come up with a sort of workforce schedule? How should I define my production plan and number of workers I need? so that I can meet the demands, and my goal is to minimize total cost. Okay? So what are the cost factors? Well, there's the production cost that comes from raw materials. There's the inventory cost. What else? There are the salaries of each employees. Hiring costs, firing costs. Okay, so I need to make sure that the total cost will be as small as possible, and I need to also make sure that I can meet total demand. Okay? Is the problem clear? All right, let's take a break. We'll continue in 10 minutes.